Hello everyone. Today we are going to have very interesting question which is related to metrics, and the problem statement is word search. And this is very important question because I tell you the importance from a very simple reasoning is that whichever software you use, for example Notepad Plus, Word, Excel, you see that there is something called search feature, right? You have a big file, you just search for a pattern. So everywhere you see this thing, like search is very important. So this problem is more or less connected to the same. In this particular problem, the statement says that we have a given m cross n grid of characters like this board and a string word. So we have this thing which has the characters and they are in the grid like two-dimensional array. So called as matrix. And we have a word which is, for example, A, B, C, C, E, D, right? Made of all these characters. We have to return true if word exists in the grid and false if does not. So word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically apparent, meaning you can go this way or this way. So for example, A, B, C, C, E, D. Okay, this is all good because you're going horizontally or vertically. You're not going diagonally. So you know which directions are allowed, right? You can go horizontally, vertically. These are directions only possible. So you cannot go vertically or diagonally, things like that. So I think the problem statement is very clear. Now, as I always emphasize in my all questions, that whenever you have any questions, any problem statements in front of you, it is very important. Take 1 or 2 minutes of time just to explain the brute force approach, and then from there jump into the optimized solution. Uh, though for this solution, I think the approach that comes in our mind is very straightforward because whenever we have a grid, if you guys know any of the graph algorithms or let's say shortest path, so whenever we have a grid like this, we always have to follow either BFS or DFS. So we will follow DFS here. And why DFS? This is a very important question. Uh, and this is very important topic also. Uh, like for example, DFS and BFS, they play a very crucial role, right? So one must know why the DFS plays a very crucial role. Why not we can use BFS here? So um, let me emphasize why DFS here. Um, so DFS is actually um, depth first search. It is used in a solution, in this particular solution, because uh, it is the best, well suited for this particular problem statement, where we need to explore all possible paths from a given starting point, right? So when we say all possible, exploring all paths in a word search problem, we need to check if a sequence of characters starting from any cell can match the given word. And DFS allows to you to explore all possible potential paths starting from a cell in all four directions, like up, down, left, right. Okay, so it follows a path deeply, character by character, before backtracking to try other paths, ensuring no possibilities overlooked. So um, DFS pairs naturally with backtracking. So for example, when exploring a path from a cell, DFS moves as far as possible along one direction. Um, and if it reaches the dead end, example, mismatch or out of bounds, it backtracks to the previous state and tries a new direction. All right. So this backtracking process allows the algorithm to revert changes. Example, restoring the character in the board and continue searching without duplicating efforts. Um, DFS is also inherently localized, meaning focusing on one path at a time. Starting from a cell, DFS recursively explores its neighbors without needing to hold multiple paths in memory simultaneously. This makes DFS efficient in terms of space, when it comes to comparing with BFS. So it only requires a stack of recursion call proportion to the length of the word. Okay. So that is the reason why we choose DFS here. Why not BFS? Because BFS is also search algorithm, but it is not suitable for problem like this. Why? Because BFS explores all neighbors of a cell simultaneously, which leads higher memory usage because it requires storing all paths being explored at the same time. I mean, at the same depth. In contrast, DFS focuses on one path, making it more memory efficient and natural for recursive problems like this. So, uh, it is very important for you to understand which problems are best for DFS, which are BFS, and why for this particular problem, word search, we are choosing DFS approach because DFS focuses on one path at a time, making it more memory efficient, rather BFS, which explores all neighbors of a cell simultaneously, and that needs more memory, higher memory usages. Okay, so DFS is ideal here. Why? Because all potential paths they are searched in an efficient manner, and then combining seamlessly with backtracking to manage state minimizes memory footprint as it was with related to BFS and matches the problem recursive nature, right, where each step depends on the outcome of the previous one. So that's the reason why we choose DFS here. Now let me quickly discuss about the solution. So, okay. So I think this is very straightforward problem as I already said. But let me quickly set what approach is coming to your mind. So let's say you have a word which is like A, B, C, C, E, D, and you got some directions, right? And you already know that you can use something which is called DFS approach. So what I can do, I can just, you know, what I can do is like we can just iterate this particular matrix, uh, meaning a one loop I loop with all the rows and then another J in nested loop with all the columns. And for every cell, for example, for every I and J, what we can do, we can make a recursive call, um, and then pass both the word and the board. And within the recursive call, what we will do, if let's say, I mean, we will start definitely from 0. So, zero index, okay, in my DFS because that is a zero index. And then we will check if zero index, meaning uh, because recursive call actually it needs some termination conditions. So termination conditions for the pattern word will be like the moment we reach the length of the word equal to, let's say, that index, we will say we return true, meaning the whole word is found. And if there are any boundary conditions reached, we just return false, because then we do not need, I mean, we need to break out that particular recursion and go to some other path. And then we save the current character um, into the um, what we should say, like we should mark the particular I and J with some special character, and then do recursive call to as it is set, like you cannot go any diagonal direction, so it is possible for you to go row plus one, column plus one, or similarly it can go row minus one, and similarly it can do column minus one, but always go horizontally or vertically up and down because those directions are possible. So without wasting time, what I will do, I'll quickly solve this particular problem and we'll see how you guys understand. So let me quickly follow the same approach. So I copy this and I write here word search. All right. SEARCH. All right. And then, all right, this is word search question. And then I will just write my main method and my input goes here, output goes here. logic goes here. All right. So what is the input? Input I can just copy from here. I have a board. So this is my input. And this is two-dimensional board. And I just need to do this because it just accepts curly braces. Don't like square brackets here. All right. And then we need string word. And this is also done. So yeah, so this looks like, all right. So I need a character array. So this is a two-dimensional character array. And because this is a character, I can just do like string because it will be better. Yeah, now this is better. And we are expecting output as true. So now what we have to do, we have to actually start the solution. So I will call some method which is, let's say, because whenever we have some question, we need to make this particular solution as a like more meaningful um, when it comes to finding this particular word. So let me write the method. It's like word search, and this word search, let's say, returns boolean, and uh, result is equals to, and let's say we are passing here board, and then we are passing here as word, right? Okay, so that's pretty much all. I also just changed this single quotes to double quotes. I mean double quotes to single quotes. There is a reason behind that. I'll quickly explain why. Okay, so now this will be char, and there it will be string. So this is fine. Yeah, so now my array is like char array. So what I have to do is, like, I just need to print here result. Okay, so this A B C C E D, if you see the question A B C C E D, this must return true when we code this. So word search, let's say this is something which we need to code. Uh, so always remember, whenever we talk about anything which is related to matrix and iteration, as I said, we have two loops. One is I, and that goes to board dot length, and then internal loop is like j, and j is number of columns. So board 0 dot length. All right. So this is my jth. And since we are picking every single element, so what we have to do, we have to start at A and recursively go in the single path, right? And then when we reach to the dead end, we just return to the previous one, and then again recursively go to this, whichever path it wants. Okay. So if now I have solution DFS uh, search, and there also what we will do, we will pass board, we will pass word, and then we will pass 0, and then we will pass, let's say, I, and then j. So what I'm doing here, if you see DFS search board word 0 I comma j, so this 0 is nothing but okay, let me quickly write this and then I just explain you it. That is condition, we return true. So this DFS search, it's actually playing a very important role here. I explain you why. So it's INDEX index. Okay, now what is happening? So this particular thing index which you see, if index is equal to word dot length, what does it mean? It simply means that whenever we are iterating going into this different depth first search, um, rather just make this method as um, mm, TFS search word. Okay. So now what I was saying, that word dot length, whatever the length of word is, if the index is equal to that word or meaning we found the complete word and we return true. All right. So this is first condition in our recursive approach. And then second one is we need to just measure the boundary conditions, right? And in any question for this, the boundary conditions are very simple. So if row is less than 0 and column is less than 0, either of these, it means it's going outside the boundary. So we just return false. Similarly, if row is greater than, it goes like this, the board dot length, or similarly column is greater than board 0 dot length. So we are returning it again. And then similarly, if let's say you have your board character at board row comma column is not equal to character at that index of word, meaning word dot caret index. In that case also we are just skipping this. So what I have to say, what I was saying here, I can write again. If row is okay, so let me rename it to more meaningful, row, and this is col. All right. So if row is less than col, this is one condition. All right. Or row. I mean, yeah. So this is one condition, and then we have row is greater than equal to board dot length. Okay. So if row is greater than equal to board dot length, or meaning what this line say, meaning if let's say the rows is going beyond this row. Okay. So that is the condition, and then or call is greater than equal to board 0 dot length. Okay. So what does it mean? It simply means that this particular index at the call is crossing this last column. In that case, this is the thing. Or at the last, what we will say, if board uh, row comma call is not equal to word row word index. Yeah. So if that is the case, what we have to do, we just have to return false, right? So I would say return false. Okay. So this is kind of some issue. So what you have to do, it's like caret index. All right. So these are my two important terminary condition. Now the logic for marking comes in. So I'll explain you again what I mean by marking. So first it's char. First I take temp is equals to board row call. All right. And then I would say I'll mark this because I already took this value, row call is equals to, and then single quotes I write hash. So this is the way we mark it, and then I will do my boolean found is equals to. Now I do the recursive DFS, and there we have to pass board, and then we have to pass word, and then we have to pass, because we already done with first index plus 1, and then third is like we have to pass a row. And so we are going like one row down, so we'll say row plus 1, and column is not changing. All right. So this is 1. Okay. And then we have similar to this another one. I need to copy. and I need to copy again, and I need to copy again. So I just need to play around with the row columns. So this is all good. And then I will say row -1, meaning it just go up. And then I would say row call +1. So it just, for example, call +1 is like if you're here, so just go here, not down, not up, it just go right side, call +1, and then we say call -1. Okay. So yeah, call -1, and it's row, row +1 call, row -1 call, and then row call +1, and then row call -1. Okay. Yeah, so this is all when it comes to DFS approach. So in every DFS call, what is happening? You are going straight to that path which is deep into the uh, mm, the last element until the boundary is not broken, or let's say you're not broken the boundary. And now we finally do row call is equals to temp, and then we just need to return found. So this is actually uh, in short the solution of this particular problem. And before I go into this, I just want to explain you the time complexity of this solution is O of m cross n, which is pretty fair because we are doing this word search recursive nested call, and then you multiply every m cross n to 4 to the power l. Okay, where l, this l particular thing is doing the recursion, and the space complexity is of L. So that's pretty much all when it comes to uh, DFS Ashwat. Let me quickly run this program, and then we will run this program on LeetCode. So I see there is something wrong, which is where it's written fails. So yes, we have to return it from here as well. Return false. Yeah, so sorry for this. And I run this, so um, it just says array index out of bounds. So it means we are kind of making some issues somewhere. Let me check. I0, I less than board dot length, I plus plus, j plus plus, 0 dot length, j is equal to 0, and then their board word. Zero ij, return true, return false, and then we have DFS search word. We're returning true here when this equal to length. In this play condition, we are just kind of returning false, and then char is this, and then we have found we have to perform DFS. So row +1, row -1, call, row call +1, call -1, call, index +1, index +1, index +1, board row call equal to temp, and return found. So I think this is pretty straightforward question. But I don't know why add index out of bound is happening. It's happening at here. Okay. So maybe I just need to row is less than, now I got it. So this is row is less than 0, and call is also less than 0. If that is the case, then it goes out of this. And you see here it is true. And if I just change it to something else, it should return me false. Yes, it returns me false. Now let me quickly copy these methods and paste it into the LeetCode and see how it runs. So we have exit as a method. So I can do something like I can just create this class, method, and then I just need to copy this whole DFS search. Okay, so now I run this. Okay, so it says some error. Let me check. Okay, so this is an error because the method exit has to be like this. Char board string. Okay, so let me remove this. So this is exit word. Okay, so now we have an extra arrow and run it again. All right, accept it and let me submit the solution. And here we go. We have the solution submitted. So I think everyone enjoyed this particular solution. Let me quickly reiterate again one more time why we are doing this. So yeah, one by one. I think everyone, let me open this whole method. So this condition is pretty straightforward. It says if the index equals to the length of the word, it means all characters have been matched successfully. So just return true. Similarly, if boundary and mismatch check is here, if row and column goes beyond boundary, meaning if let's say row here, which is this. So if row's index is like going beyond this first row, it means less than 0. Similarly, column is less than 0 beyond first column, and row goes beyond the board dot length, and column goes greater than equal to board dot length, 0 dot length. And then similarly, if these are not matching, this condition is simple, like whatever word you are searching at, that index is not found at particular board, then we return false. And this code you see here, this is a pure recursive code, what we use to do every time in the recursive call. In recursive call, I mean the DFS, for example, we just need to find out which directions we have to move. So index plus one, and you see here, this is the index which is maintained to match when the word length, the whole word is found. And these are directions. So for example, row plus one column, so you are moving down because row plus one and column is not changed. Row minus one, meaning you are moving up. Then row col plus one, you are moving right and you are moving left. This is how exactly it works. So this temporarily stores the character in a variable temp, right? And marking the cell as visited by replacing its value with hash. Why we are doing this, line number 42, it's very important. This prevents revisiting the same cell during the current path. Okay, so you're not revisiting this cell again and again, and that is very important when you solve. And then why we are doing this, like 49, this restores the original character in the cell after the recursive exploration is complete. Then ensure this other path can still use this call. Okay, and then at the final stage, we just spark this return, whatever return we have. So yeah, that is pretty much all. Let's talk all about the time and space complexity as well. So as I said, time complexity of this solution would be um, O of um, yeah. So time complexity would be O of m cross n cross 4 to the power L, right? So where uh, this L here, right, it is the number of recursive calls. So because we are making four recursive call here, so it will be the 4 to the power of L. So let me add here time complexity, and I think it will be easy then. Time complexity is O of m cross n cross 4 to the power L. All right. So I see you in another video. Thank you very much.